Hi, I'm Satyam Agrawala and this is my presentation for final project. My architecture has a 16-bit word size. The memory is byte addressable. There are 16 general purpose registers of size 16 bits. There are 2 special registers, program counter, instruction register, and the instruction set is MIPS-like. My special feature is hardware multiplier and barrel shifter. These are my general purpose registers. The stack pointer, register 13 is reserved for stack pointer, register 15 is reserved for return address. My ALU supports 8 operations: add, subtract, and, or, nor, less than sign, less than unsigned, equal to, and the outputs are equal to 0, used for branch, and then cout. The instruction set has 4 formats, 4 types. There's the R type for ALU instructions, where are 4 bits for opcode, 4 for register, 4 for register, and 4 for function code. Then there's I1 type, 8 bits for immediate, I2 type, 4 bits for immediate. This is for load word and store word. And then there's the jump type, which has 12 bits for the target. I have a total of 24 instructions. These are all the ALU instructions. There is mult, and then there's shift instructions also. And these are all the ALU immediate instructions. There is branch instruction, there is load word and store word, and jump and link. My FSM is a melee FSM. It has 7 states. All my state changes and register changes happen on clock rising edge. There are 2 states for instruction fetch. Once the instruction is loaded from memory, load IR is set. Then there is a decode and execution state. In this state, load PC is set for ALU, ALUI, jump, load word, and store word instruction. And register write is set for ALU, ALUI, and jump and link instruction. Then there is a branch state. Here, the load PC is set for branch instructions. Then there is load and store word. In this, register write is set if it is a load word. And then there is a multiply state. This is my block diagram. You can take a look. Okay. My novel feature is the multiplier. It does both signed and unsigned multiplication, and it can get high and low values of the product. The algorithm is like this, that I set the accumulator to 0 and load multiplier and multiplicand to register. If the multiplier is 0, then I just set a done flag to the FSM. If the multiplier last bit is 1, then I add the multiplicand to accumulator. This is a 32-bit addition, and then shift the multiplier right by 1 bit and multiplicand left by 1 bit, and then jump to step 2. The barrel shifter supports SRL, SLL, and shift right arithmetic. The algorithm is exactly same as in class. This is my sample assembly code. Instructions are preceded by a .text, and data is preceded by .data. This sample code is just going to load address in int1, a load address of int1, and store the value FFFF in t1, and then shift it right, and then shift it left, and then shift it right arithmetic, and then store that value back in int1, and do this in a loop. Okay, so now I will show how to run this assembly program on my hardware. I'll start with generating a MIP file using the assembler. So that worked fine. So this is the MIP file which I got, and it shows all the instructions as well as the disassembly on the right side. After the end of the instruction, these are the data values, and if we compare it with the assembly, this looks correct. The first one is the load address, which is a pseudo instruction which got expanded, and the rest all are fine. So now I will run my emulator to debug this MIP file. So I'll use GDB for that. I'll set a breakpoint, and I'll just run it for 4 instructions. And now I can show you how my trace file looks. So my trace file shows that 4 instructions has been run up until now. It shows the PC values for each of those instructions, the disassembly, relevant register values at each instruction, and also the memory which got on the stack which gets modified in a given instruction. And you can see the red indicates that the register got modified in the last instruction. So now I will run it on the hardware. So I have already loaded the MIP file on the hardware. So let me just reset it. I want to start with saying that these 7 segment displays will show the PC of the current instruction being executed. This will show a bunch of things starting with instruction register, register data, mem data read, mem data write, and so on. The green LEDs and red LEDs are used to display input values to the FSM as well as control lines from the FSM. The last three LEDs here will display the state of my FSM. So let me just step through it to show what happens. So right now the mem data inverse bit is high and I'm in state 0. So I'm expecting that once I start stepping, I should move to state 1. So I move to state 1. Now when the data inverse bit goes lower, I'll move to state 2, and load IR will also be set to 1. So load IR was set to 1, and you can see that load IR has been set to a value of 2600. If we compare it in the MIF, that is 2600. So now I'll just step through a bunch of instructions just to show that PC is getting incremented, the IR is getting loaded correctly. So right now I'm in the fourth instruction, which is an OR instruction. This is going to load the value 40 in register T0. So let's just see if that happens. Right now I'm in state 2 and my register write enable bit has been turned on as 1 and PC has been set, load PC has been set on as 1. So the moment I move to the next state, I should see that the value of T0 is set. So the value of T0 you can see has been set correctly, 40, and PC has got incremented. So now I'm just going to run this program, and you should see that the value a value of FFFF gets loaded in register T1, and then it starts shifting to right, then to left, and then right arithmetic. I'll increase the clock, decrease the clock speed so that you can see it. I'll just start the program. So you can see that the register T1 has a value of FFFF, and then that value shifts to right first, then to left, and then right arithmetic. So this is all I wanted to show. Now I am going to show my final program. First I'll load the MIF. So you can see the serial port here, and so I'll just reset it and set the clock speed back to 0, the divider limit to 0, and just reset it and start it. So this is asking me to enter the first number, so I'll start with something simple. The product is correct, -6. If I do something big, let's say, so that also works fine. If I do something really big, so that gives overflow. Now I'm going to load another MIF file which will show my novel feature. It will be exactly the same program as the final program, except that now it will use a mult instruction to perform multiplication. So I'll just reset this first. And reset it and then start the program. So now it's asking me the same question, enter first number. So let's say if I try something like 256 into 256. Now this value is 2 to the power 8 multiplied by 2 to the power 8 will be 2 to the power 16, which exceeds the 16-bit limit. But I can see the 32-bit value in hex as 0001 0000, which is the correct value. So let's just try a negative number maybe. Let's say -32768 into 2. So while the 16-bit value here comes as 0, but the hex value which is -2 to the power 16 is correct. So that's all I want to show. Thank you.